This is a video for AQA Further Pure Mathematics, Matrices section 3.5, Determinants and Transformations. We've already met the idea of matrices producing transformations. So for example, we have a shear matrix here, the matrix 1, 2, 0, 1, and if we were to look at its effect on one point, for example point A there, which is 0, 1, we can see that 0, 1 maps onto 2, 1. So A maps onto A dashed, as shown on the diagram, etc. We can calculate the area of the original object. Obviously it's a square size 1, so the area of ABCD is 1 unit squared. The area of A dash B dash C dash D dashed, well, that again is a parallelogram of width 1 and height 1, so it has an area also equal to 1 square unit. This diagram shows an enlargement, this time the enlargement scale factor 2, and if we look at the areas, well, the original of course is still 1 square unit. A dash B dash C dash D dashed, the image is now 2 by 2, so this is 4 square units. So we've got here an enlargement which has enlarged the area by a scale factor of 4. As you know, that in an enlargement we have got linear scale factors quoted, so the area is going up by that value squared, so 2 squared is 4. If we look at the determinants of each of these matrices, if I call this one matrix M1, then the determinant of M1 is equal to 1. And remember that the area scale factor was 1. This one, matrix number 2, and the determinant of M2 is equal to 4. So it appears that the area scale factor is equal to the determinant of the matrix. And that's something that we can confirm quite easily by looking at a general matrix A, B, C, D. So as shown in the diagram here, you can see that the new figure A dash B dash C dash D dashed, and that's produced by the image of the matrix for the original object multiplied by the matrix A, B, C, D. So you can check quite easily that that produces this matrix, which is as on the diagram, and that the area of the parallelogram in the diagram is AD minus BC. But of course that is just exactly the same expression as we have for the determinant of the matrix M. So therefore the determinant of M must be equal to the area scale factor of the transformation. If the determinant is negative, as in this case, so here we've got a matrix M, and this time the determinant is equal to negative 2, you can see that the area is clearly multiplied by 2. So what about the negative sign? Well, that's something to do with the orientation of the object. So the diagram shows the original object as being labelled in a clockwise direction, O, A, B, C. But if you compare that to the direction of labelling in the image, it goes anti-clockwise. The fact that the orientation has changed means that the transformation must have within it a reflection. So for example, we could consider this transformation as being firstly a stretch parallel to the y-axis, and then that would put in a subsequent point here, let's call it B double dashed, and then a reflection in the y-axis produces the final figure. So that reflection is indicated by the fact that we've got a negative in the determinant. In summary then, determinants of 2 by 2 matrices give a signed area scale factor. So an area can't be negative, however this is significant because it's indicating the fact that we've got a reflection taking place within the transformation. So if you consider these, the reflection has got determinant -1. So I'll just write det at the top of this list, -1 here. Enlargement scale factor 3, determinant is equal to +9. And this is a rotation. If you check the determinant of that, it is +1. So the reflection giving a negative determinant, the other two enlargements and rotations where the orientation of the object is going to stay the same, they have got positive determinants. If the determinant is 0, as is the case here, then all points map onto a straight line, and so that the image has got 0 area. You can see here that A is mapped onto A dashed, B onto B dashed, etc. And they're on this line. We could take a general point xy, and that will map onto x plus y and 2x plus 2y for any value of x and y. So you can see that y dashed is equal to 2 multiplied by x dashed, so that all points map onto the line y equals 2x. And that's this red line here. So when the determinant is 0, all points map onto a line, giving us a 0 area for the image. In 3 dimensions we have a similar idea. This time, of course, instead of a unit square, we've got a unit cube, and that's transformed onto a parallelepiped. In other words, a 3-dimensional parallelogram, as it were, but a 3-dimensional shape. The determinant of the 3x3 matrix gives a volume scale factor. The fact that it's a signed volume scale factor again means that the orientation of the vertices will be the same if the determinant is positive and reversed if the determinant is negative. So for example, consider this determinant here, or the determinant of this matrix, which we can clearly see is going to be -1 multiplied by the determinant of this little 2x2 matrix here. So the determinant of this matrix, if we call it M, the determinant of M is equal to -1. And we can see that here we've got a reflection in the YZ plane. So the original object is now reflected into this new one. That completes this video on determinants and transformations. In the next one we'll be looking at inverses and transformations.